Chemical reactions occur everywhere. Some are slow, while others are rapid. A smoldering log is an example of a fairly slow chemical reaction as contrasted to the rapid reaction of the aluminum in a flashlight bulb. Chemical reactions are dangerous if too rapid and useless if too slow. To control them, one must understand the factors that affect the rate of reactions. Let us consider some of these factors. An iron wire, even when heated, reacts very slowly with the oxygen present in air. In fact, so slowly that no change is perceptible. But when I plunge the hot wire into a cylinder of pure oxygen, the iron bursts into incandescence. In this cylinder, only oxygen molecules are present. Therefore, the opportunities for contact and for reaction between oxygen and iron are greater than in air, in which only about 1 out of every 5 molecules is an oxygen molecule. This explains why the reaction of iron in air is so slow. Similarly, when the draft of a furnace is shut off and the check damper is opened, the rate of combustion diminishes because the supply of oxygen to the coals is decreased. Let us determine more precisely the effect of concentration on the rate of a reaction. Each of these 2 vessels contains the same amount of sulfurous acid and starch. I will add 50 cubic centimeters of iodic acid to the solution on the right, and twice as much, or 100 cubic centimeters, to the solution at the left. Note that the reaction in the vessel containing the larger amount of iodic acid is completed in 12 seconds, whereas the one with half this amount requires 23 seconds. Doubling the concentration of the iodic acid doubled the speed of the reaction. An important aspect of reaction velocity is seen in reversible reactions. Let us, for example, force steam over metallic iron. The steam and iron react to form iron oxide and hydrogen. But if the hydrogen is forced over the iron oxide, metallic iron and steam are regenerated. The second reaction is the reverse of the first. If both hydrogen and steam are free to diffuse into the mixture of iron and iron oxide, both reactions take place simultaneously. Under such conditions, the rates of the opposing reactions depend upon the concentrations of the reacting substances. By concentration, we mean the number of molecules of a substance per unit volume. We shall represent relative concentrations by lines. We can increase the concentration by putting more molecules into a given space, or by decreasing the volume occupied by a given number of molecules. Let us consider a reversible reaction between gaseous substances. When steam and carbon monoxide are in high concentration, they react rapidly, as is shown by the length of the arrow and the large number of molecules moving toward the right. As a result, the concentration of these substances decreases, and the rate of this reaction diminishes. But the products of the reaction, hydrogen and carbon dioxide, accumulate, and as a result of this increase in their concentration, there occurs an increase in the rate of the reverse reaction, that is, of the reaction to the left. Note that the original fast reaction to the right is slowing down and the other is speeding up. Eventually, the 2 attain equal speeds. This condition is known as chemical equilibrium. At equilibrium, both reactions are going on, but no change in concentration occurs. Now we add more steam to increase the concentration. This increases its rate of reaction with carbon monoxide. Consequently, hydrogen and carbon dioxide again accumulate, and the rate of the reaction to the left also increases. As before, the rates of the two reactions will eventually become equal. But we see by the lines representing concentration that the addition of steam has shifted the equilibrium position to the right. Now let us remove some of the hydrogen to reduce its concentration. The velocity of the reaction to the left is lowered momentarily, and steam and carbon monoxide accumulate more slowly than they react. The resulting decrease in their concentration slows down the reaction to the right until the two reactions again attain equal speeds. The removal of hydrogen, like the addition of steam, shifts the equilibrium position to the right. Thus far, we have considered reactions at constant temperature. But temperature change also has an important effect on the rate of a chemical reaction. Let us again use the reaction between sulfurous acid and iodic acid to investigate the effect of temperature. The solution at the right will be kept at 25 degrees and the one at the left at 35 degrees. I shall add the same amount of iodic acid to each solution in order to have the same initial concentrations. The reaction at 35 degrees is completed in 10 1/2 seconds as shown by the color change, while the one at 25 degrees requires 24 seconds. Note that a 10-degree rise in temperature doubles the velocity. To understand this phenomenon, it must be recalled that only 1 out of billions of collisions between molecules results in chemical change. This suggests that only the fastest moving molecules are capable of reaction. Most of the molecules of a gas, as shown by this distribution curve, have velocities close to the average velocity represented by this line. A few move very slowly and a few very rapidly. The area below the curve represents the total number of molecules. The minimum velocity that molecules must have for the reaction we have selected is represented by this short line. If the temperature is raised 10 degrees, the average velocity is increased only 4%. But the number of molecules having velocities great enough for reaction is increased 100%, as shown by the fact that the area to the right of the minimum velocity line is twice as great as it was at the lower temperature. Molecules moving at velocities below that necessary for reaction rebound without reacting when they approach each other within an area here indicated by shaded circles and commonly called the sphere of influence. But when molecules of high velocities collide, the spheres of influence interpenetrate and a chemical reaction occurs. High velocity molecules may produce another equally important effect. To explain this, we choose another mode of representation which emphasizes the vibrations between the atoms within a molecule. When a high velocity molecule strikes another, it may increase the vibrational energy of the latter and weaken the bond between the atoms. When two molecules with weakened bonds collide, reaction is likely to occur. We have represented in simple form very complicated phenomena which accompany chemical change. This simplification has been necessary to make clear